So now we're going to hop over to chapter 3, section 5, because it applies to what we're doing. We're looking at limits at infinity. These are different than infinite limits. So infinite limits, we're saying, oh, a limit approaches infinity, but we're saying, what if the x value is approaching infinity or negative infinity? So there are three cases. If you have a rational function, you could have a rational function that's top heavy, bottom heavy, or a tie. And so finding a limit as it approaches infinity or negative infinity is just as simple as finding the horizontal asymptote. Because if you think about those graphs, the y value that the graph is approaching is equivalent to whatever that horizontal asymptote is. So if the function is top heavy and you're thinking of like direct substituting in infinity, which is not a real thing we can do, but we can kind of picture that. I'd have a big infinity divided by a little infinity, or in other words, there is no horizontal asymptote. This thing is climbing toward infinity, or if one of these were negative, climbing down toward negative infinity, and that would be the limit. Does the limit exist? No. Just like last set of notes yesterday, we're just saying how it does not exist. If the function is bottom heavy, the horizontal asymptote is 0, and so a tiny infinity, if there's such a thing, divided by a huge one that's growing faster, is 0. So that limit does exist, and its value is 0. And if the rational function has a tie, then the horizontal asymptote, since you're balanced, top and bottom, should be whatever the coefficients divide out to in front of those highest coefficient terms. So this is 3/4 in this case. Again, same thing is true for negative infinities as we're approaching positive or negative infinity. So find the following limits. So all of these you can see are rational functions with the exception of number 7. All right, so first one, find the limit as x approaches infinity. This is a tie. The answer is 4/3. These are really easy limits, so don't overthink them. As we approach negative infinity, we still have a tie. The limit is 1/5. Doesn't matter whether we're approaching infinity or negative infinity in this case. This one, bottom heavy, the limit as x approaches infinity is 0. Top heavy, since these are both positive terms, we're plugging in positive infinity, heading toward infinity. The limit as x approaches negative infinity of this function, remember you can separate this out. The limit as x approaches negative infinity of 5, which is a constant, is equal to 5, minus the limit as x approaches negative infinity of x plus 1 over x minus 2. So this limit, its horizontal asymptote is 1. It doesn't matter that you're approaching negative infinity. It's not going to be negative 1. Think about that graph. It has a horizontal asymptote of 1 all the way across. Doesn't matter which side we're looking at. Anyway, so 5 minus 1 is 4. That's the limit value as x approaches negative infinity. Or you could add these together if you wanted to, and then find the horizontal asymptote that way, but I think that takes longer. 6 is not truly a rational function because the definition of a rational function is a polynomial divided by a polynomial. But we can still think about what's happening. What goes on with cosine of x all throughout its graph as you approach infinity? It's going to stay between -1 to +1, right? Those are the extreme values and everything in between. It could hit 0, any decimal in between. And then what's happening out here? If I'm thinking infinity in for x plus pi, I would just have this big infinity. So in the grand scheme of things, if I have 1 or -1 or some decimal in between, and I'm dividing by a huge number, ultimately that's going to be 0. Whether it's slightly above or slightly below the x-axis is irrelevant. Those values are going to be so insignificantly small that they're practically 0. What if it's just sine x, or what if this would have just been cosine x? Well, that's different because I know that these values are going to be between -1 and 1. Think about the sine graph. But there is no limit, and there is no limit to stop. Like, it's going to continue to have that negative one-to-one fluctuation. And there's nothing that I'm dividing the function by that's going to force it to get smaller and smaller and approach a number. So this limit does not exist. And it's because it's oscillating. Now, we said the first example I gave you of oscillating was like a function that was like nice and easy, and then it went crazy like this, and then it like kept going on. That's oscillating. But what we mean by oscillating in this sense is if we're headed out toward infinity, it never slims down. It never narrows down and gets to something. Number 8, set of parentheses must have gotten cut off. I'm going to take this limit in 2 sets. Limit as x approaches infinity of 3 is 3. The limit as x approaches infinity of x squared plus 1 over x cubed, bottom heavy, is 0. 3 plus 0 is 3. All right, let's do some multiple choice AP problems. You can see which test this was from. So these are a bit old, but you know, some of these are classic types of problems, and you'll see them on any given year. F of x equals natural log of x when x is between 0 and 2, x squared times natural log of 2 when you're between 2 and 4. Then the limit as x approaches 2 of f of x is what? Well, this is a piecewise function, so I want to take a look at this. If I'm plugging in 2 here, I can say f of x on the, let's see, so if I'm plugging in 2, I'm to the left of 2 right here. The limit, now do I have to plug in my notation and stuff? No, but I'm just trying to describe what I'm doing for you. Like multiple choice, the amount of work you show is up to you. 2 from the left into natural log x is equal to natural log 2. So the left-handed limit is natural log 2. What happens if we plug this into the right? Approach 2 from the right of x squared natural log 2. Now you're getting 2 squared is 4 times natural log 2. If you want to get fancy and remember all of your log rules, that's this guy. So check out your options. Natural log 2 and 16 both show up, but you're getting different values on the left and the right, so non-existent is our solution. There is no limit as x approaches 2 in general of f of x. The graph of the function f is shown in the figure above. Which of the following statements about f is true? We're looking for true statements, so we just have to go through them all. The limit as x approaches a of f of x, which looks to be 2, is equal to the limit as x approaches b. That is non-existent. It's not a. Limit as x approaches a of f of x is 2. That seems correct to me. I can do a quick run through of the others. Limit as x approaches b is 2. No. Limit at b doesn't exist. No. Limit at a doesn't exist. No. So b was correct. What about this last one? Let's see. The limit as x approaches 1. If I do direct substitution, I get 1 divided by natural log of 1. What's that equal to? 1 divided by natural log of 1. Does natural log of 1 exist, first of all? Think about that natural log graph. Remember, it had a vertical asymptote at 0. And so, yeah, natural log of 1 exists. It's something. 1 divided by this value, natural log of 1. Let's see. No, natural log of 1 is 0. So that's unbounded. Sorry, that's undefined right now. Now, when we get to, so what are my choices here? 0, 1 over e, 1, e. All I can choose right now is non-existent. When we talk about L'Hopital's rule, which a couple of you took AB calculus last year, so you've heard of L'Hopital's rule. Take the derivative of the top divided by the derivative of the bottom. We'll be able to work more on that. But for now, we're just going to leave it at this. 1 divided by 0, and that's non-existent.